Okay, so we're Team 11. I'm Marybel Hernandez, this is Jonathan Gomez, and Orestes Castro. And this is Project 2, and we're going to be talking about power transmission system design. Our problem statement starts off by telling us that the power is going to be 7 horsepower, the input speed is 1500, and the output speed is 125, which gives us a ratio of 1 to 12. And our input and output direction are opposite. Our input and output shaft have to be parallel and aligned, and we need a high precision gearbox, which caused us to select helical gears. When researching, we found this product, helical speed reducers, which is very similar to our project, and it has a high range in horsepower that goes up to 80 horsepower, and it has applications in molding, extruding, and lamination. This is a diagram of our shaft, of our power transmission, and it has four gears in the first stage and 5 gears in the second stage for a total of 9. We designed the input, the output, and the connecting shaft. And here we have the combination of teeth that we selected and the corresponding angular velocity, torque, and force transmitted. Some of the assumptions that went into making this was they are listed here, and one of the main ones are the material, which we selected grade 3 carbonized hardened, and as a factor of choosing that material, the life was selected to be 10 to the power of 7 revolutions, and the reliability was 99%. Another assumption that we made was the quality was 10. And here is the list of the safety factors for the bending and the contact. Gear 7 is the one with the smallest amount of teeth, and that's why they have the smallest safety factors, but it did surpass our minimum, which was 1.2. So it was a safe design. And now I'm going to pass it on to Jonathan, who's going to talk about shaft design.
So for the shaft design, we use different methods and different theories to calculate the optimum sizes for the diameters. We use the modified Goodman and the Gerber failure theories that uses the von Mises stresses. We have some equations there that we used in our calculations. And for the slopes and deflections, we use the singularity method. The main characteristic, the main values that needed to be calculated in order to perform these calculations are the bending moments for each shaft, the maximum bending moments, and the maximum torque for each shaft. This is the results for the factor of safety for 3 shafts. All of them are selected to be 0.75 inches in diameter, and as we can see, both the Goodman theory and the Gerber theory, the factor of safety is above 1, meaning that it's a safe design. And the material we chose for all 3 shafts, it's 1045 steel, which gave us the right properties to get the correct and safe values. For the slopes and deflections, we use the singularity method. Shaft 1 and 2 is 4 inches in length, and shaft 3 is 8 inches in length because it supports 2 shafts instead of 1. And these are the critical points in which the calculations was calculated, the deflection was calculated. As you can see, the maximum deflection is 3.89 times 10 to the negative 2, which is it's not a significant deflection, meaning that the design is a safe design. Now I'm going to leave you with Orestes to talk about the bearing selection.
Alright, so for the bearing design, there are 2 types of bearings. There are rotor ball bearings and rotor taper bearings that we could have chosen for our design. Since we had helical gears in our design, our most ideal bearing would be the tapered bearing. And with the reaction forces, we could get the vector additional forces, and with the radial action force, we could get the assumed catalog C10 force with a K factor of 1.5 as the assumption. And with that, we could go, once we get the C10 force, we could go into the catalog, choose our tapered bearings, and with the forces, the new C10s given, we could then do a trial and error and see if the C10 force given is higher than the assumed C10, and with that, we can make the assumption that these 2 bearings are safe enough for our design. For the bore diameter of 0.75 inch, we apply the same applications, and from that application we got 3 tapered bearings that were safe in our design, and from that we chose our most cost-effective bearing. And for the bore diameter of 5/8, we did the same application, and from there we got 2 tapered bearings that were safe for our design, and with that we picked the most essential cost-effective for our design. The cost estimate of the cost estimate for the shaft was 1045 steel, which it was 6 feet long and 1 inch in diameter, and it cost $86. Our total gear estimate, which was 9 gears in total, was $1,234, and our total tapered rotor bearings cost estimate was $1,282, which it was 16 bearings in total, and that comes out to our total cost of $2,602. With the maintenance, you should definitely check if the teeth have wear or if the shafts are bent to minimize vibration. And also you should replace the seals and bearings to maintain the lubricant inside the casing, and also change the lubricant frequently to keep the system good. And I'm going to pass it on to Jonathan Gomez, which he's going to explain the application.
For the applications, we chose the portable earth drill, which has similar characteristics with our design regarding horsepower, output, shaft speed, and space constraints. This drill is used in specific types of soils which require low horsepower and low output speed, and which matches our design. This is an animation of our design. As you can see, the 9 helical gears, the input and output shaft line transmitting 7 horsepower throughout the system, and the input shaft rotating opposite direction as the output shaft. So in conclusion, our analysis was based off of trial and error calculations, using different diameters, different values to have the optimum performance on our components, using modified Goodman and Gerber failure theories for optimum shaft diameters, and using the AGMA procedures for the gear design, as well as the Boston gear catalog and the Timken bearing catalog selection. So overall, our design it's a safe design that met the requirements and the criteria given in the problem statement. Thank you.
Gangster.
Win.